Homework 3 was due 20 minutes ago. What I will do is, instead of going over the solution to homework 3 right away, what I will do is I will post homework 3 solution later today, and give you some time to review it, and then come back on Wednesday lecture. I will spend maybe 20-30 minutes going over the solution of it. Okay? And meanwhile, just a reminder, midterm text is next Wednesday. So later today or tomorrow, I will release quiz 1, 2, 3, which cover problems similar to the ones in homeworks 1, 2, 3. So you can use those quiz 1, 2, 3 to kind of get a taste of what the midterm will be like. Okay? Any question on that? No? Any question? Oh, go ahead. Both, of course. SQL and the results, of course. Yeah.
Does the midterm cover up until homework 3?
Yes. Midterm will be whatever we have covered from homeworks 1, 2, 3. In other words, midterm will not include the stuff on functional dependency, the discussion after SQL. Okay. For some reason, this projector is not showing. Sure.
There.
Ah, okay. Any more questions? Okay, if there's no more question on that, any question on your project? So, by the way, we haven't set up a deadline for the project yet, right? So I said I'm gonna do a poll to figure out whether you wanna have it due before the spring break, in the middle of the spring break, or after the spring break, okay? So to make it simple, okay, I'll give you only two choices. One is to make it due before the spring break. Let's say the Sunday before the spring break. Okay, that's option 1. Okay, option 1, Sunday before spring break, right before spring break starts. The other is the Monday after spring break, right after you come back from spring break. Option 2. Okay, how many go for option 1? Okay. How many go for option 2? All right. Okay. For those who voted for option 1, option 2 is not a bad choice. You can still have it done by Sunday, right? So, right, if you voted for Sunday, you can get it done by Sunday, right? You just ignore the actual week, so you can enjoy your spring break. Okay. So, project will be due the Monday after spring break, which is by your choice. So don't come back from spring break and ask for extension saying, oh, I had my spring break, I don't have time to work on the project. That's what you voted for, right? So, so take the break and really, use the break to catch up on that project implementation. So, which means once we come back from the spring break, we have about a month left to do phase 3. Okay, so phase 3 will immediately kick in on that Monday, and on that Monday coming back from spring break, I will cover GSP and web programming. So basically prepare you to get ready for the implementation of phase number 3. Okay? And so far, any question on the project on phase 2? No? Okay, seems like everybody is doing well. Now, let's continue the discussion on functional dependency. Like I said, one more time, I will release the solution to homework 3 after the lecture today, this afternoon, so that you have some time to review it. Instead of me just going over the solution, I want you to have a time to review it, because SQL will be, of course, an important part of your midterm test, right? So I want you to spend time, review the solutions, so that I can speed up my review of the homework 3 a little bit on Wednesday's lecture. Okay, so this coming Wednesday, I will spend 20-30 minutes to review those, and you can look at the solution I have prepared and think about which one problem or which few problems you want me to discuss, right? So on Wednesday you can let me know. So obviously I don't have time to go over each one of them, so I will probably emphasize on maybe 2 or 3 SQLs to kind of dissect those and explain how those were constructed. So coming into Wednesday lecture, you want to look at the problem and select maybe 2 or 3 that you would like to be discussed. Let me know on one lecture. Okay. All right. That being said, let's continue the discussion on function dependency. So we're almost done with the discussion on functional dependency. So last lecture we stopped at the discussion of attribute closure. So from this example, if I may refresh your memory on this contract schema, we use this simple example to illustrate a couple of things. One is how do you infer additional functional dependencies from a given set of functional dependencies as the input. Okay. Secondly, in that step, in that procedure, we discovered new keys, new candidate keys for the given schema. Okay. We discovered new candidate keys for the given schema. We also studied how do you do the translation between, a user specification constraint to functional dependency, and to go from functional dependency back to a user constraint, right? We study how we go both ways. Okay? How do you look at a functional dependency? How do you interpret a functional dependency? And how you go from a user specified constraint to a functional dependency. Okay? So those are the things we covered using this particular example. And in that discussion, an observation arises, which is the following. Given one or more attributes, that one or more attributes may determine some other attributes from your schema. Like look at this example. Given C is contract ID. We know contract ID determines everything else. As soon as we discover that C determines everything else, we realize C must be a key. Okay. So given this observation, and also the fact that JP determines C, we can immediately tell that JP is another key. In other words, by looking at what set of attributes a given set of attributes may determine, will help us understand what are the keys of a given schema. Right? So that's kind of the observation you can learn from this example. So can we formalize this argument? And determine quickly whether one or multiple attributes is a key or not? Can we do that? So the answer is yes. We're going to introduce this concept called attribute closure and use that to facilitate our discussion, to answer that question I have just asked, which is given one or multiple attributes, can we quickly determine if that one or multiple attributes is a key or not for the given schema? Can we do that quick? Can we make that decision quickly? So the concept of attribute closure is as follows. So attribute closure refers to the set of attributes, an input attribute or a set of input attributes can determine with respect to a given set of functional dependencies. You can do this by computing the closure of the functional dependencies. If you still remember this concept of closure, so given F, of course, with respect to a schema R, you can compute this closure of F. For example, give you a simple example, if R is simply ABC with 3 attributes, my F is, let's say my F is A determine B, and B determines C. Suppose that's my F. What's the closure of F in this simple case? Closure of F is all the functional dependencies that you can derive from a given set of functional dependencies. Right? So can someone tell me what's the closure of F for this simple example? This really simple example. Go ahead. Yeah.
Would it be A determines B, B determines C, and then A determines C?
Excellent. Using transitivity, you can discover this new functional dependency that's not part of the original functional dependency. At this point, dependencies you can derive from this, which is precisely the definition of closure of F, meaning all possible function dependencies you can derive from an input function dependency set. Okay? Does that make sense? Now, if you can derive the closure of F, now the closure of attributes is essentially all the attributes can be determined by a given attribute or given set of attributes with respect to F closure. So for example, what's the attribute, by the way, attribute closure of a particular attribute is just written as we are using similar notations, using the superscript of plus over that attribute of that set of attributes. So the attribute closure of A is all the attributes that can be determined by A with respect to the closure of F. With respect to the closure of F. So that means that if you look at the attribute of A, obviously A determines B, right? And A also determines C. That makes sense? And there is also a trivial function. By the way, in the closure of F, we ignore all trivial function dependencies. We ignore all trivial function dependencies. What are trivial function dependencies? Well, for example, A determines A, B determines B, C determines C, or AB determines B. There are many such examples. Those are what we call trivial function dependencies. Does that make sense? From the trivial function dependencies, you can actually discover another attribute from the attribute closure of A, which is A itself. A determines A itself. So the attribute closure of A with respect to F closure is ABC. In this case, do you follow this discussion? Yeah. It's important, by the way, to compute the attribute closure of A with respect to the closure of F, rather than compute, attribute closure of A with respect to this. For example, if you calculate the attribute closure of A with respect to F, what do you get? You get only AB. You get only AB. You don't get A determines C. Do you follow that? Which leads to a wrong conclusion, right? If you do this, you know what's the conclusion? A is the key. Why A is the key? Because by the fact that attribute closure of A has ABC means A determines all attributes in the schema of R, which by definition makes A a super key. And the only subset, the only proper subset of A is empty set, which cannot be a super key, which makes A a key by the definition of key. By the definition of key. All of you follow this argument? Whereas if you calculate the closure of A with respect to F, you get the wrong conclusion that A is not a key, which is wrong. You got the conclusion that A is not a key because you thought A does not determine C. A only determines A and B. You get the wrong conclusion by doing that. Do you follow this? Yes? Okay. Let's do another exercise, right? What's the closure of B? Can someone tell me? What's the closure of B? In this example, what's the closure of B? Go ahead. BC. BC. Excellent. Because B determines C, and B, the trivial function determines B determines B. Okay. What's the closure of C? And I got another one. Help me with this. Go ahead. C. Yes. C just determines itself, doesn't determine everything else. So using this simple example, you kind of understand the concept of closure for attributes, right? By the way, the concept of attribute closure can be applied to a set of attributes as well, not just to a single attribute. For example, what's the attribute closure of A and B? What's the attribute closure of A and B? What this means is all attributes can be determined by A and B together with that to closure of F. That's the definition of the attribute closure of AB. With that being said, can someone tell me what's the attribute closure of A and B together in this case?
ABC.
ABC. Can you explain? You answer a little bit.
Because A can determine ABC and B can determine BC, so just a combination of them. So
yeah. So your explanation is correct, but it actually it's an overkill statement. Okay. All you need to say is AB determine A is a trivial function dependency, right? Mm-hmm. And by the fact that A determine ABC, which we already know, using transitivity we know AB determine ABC, henceforth we got this conclusion. Does that make sense? So that's an easier argument you can make. Now, I'm going to continue to ask you to answer the following question, which is AB a key for schema R?
no.
No?
It's
Excellent. Can you tell me why?
Because if you break it apart, then they.
Okay, let me ask you this.
Because A is a key, therefore together they would be a super key, right?
So the fact that AB closure is ABC means that AB is a super key. AB can determine everything else, so AB must be a super key. However, just as he said, A is a subset of, so A is a subset, a proper subset of AB, and A is also a super key, which means that AB is only a super key, but not a key. So far, so good? Okay? So this is the importance of attribute closure. This simple example illustrates the importance of attribute closure, which is to help you find keys and the super keys of your schema. Keys and super keys of your schema. However, if we look at this particular algorithm, right? By the way, what we did is algorithm. An algorithm is nothing else a procedure you apply to solve a particular problem. Our problem is the input is R and F. This is our input, and maybe together with attribute X. This is the input. X is one or multiple attributes of R. The output is to find the attribute closure of X. Right? That's the input of our algorithm. Input is R, F, and X, where X is a subset of R, and output is attribute closure of X. Right? That's the input and output, and we just described an algorithm to solve this problem. The algorithm is very simple, which is you go from F to F closure, then you just check X against F closure. You're done, right? That's what we said. Is that clear? So that's the algorithm. Is this the best algorithm though? The answer is no. Attribute closure, functional dependency closure, meaning F plus, can be really expensive to compute. In this simple example, it's fine. But if I go back to the last slide, if you recall the discussion from last week, there are many more dependencies you can actually derive from F. The key observation is not all of them will be relevant to the computation of X closure. Not all functional dependencies in F closure will be relevant to the computation of F closure. Some of them will be relevant, but not all of them will be relevant. If you compute F closure and then compute X closure, the attribute closure, you may end up doing a lot of wasteful work. You see that? Right? Some attributes have nothing to do with X, yet in the computation of F closure, you need to derive those functional dependencies, even though they are not useful at all towards the computation of X closure. So it's overkill in some sense. It's kind of like give you an analogy or metaphor. It's like I ask you how to go from Salt Lake City to Boston. How to drive from Salt Lake City to Boston. Okay? How to drive from Salt Lake City to Boston. And in order to solve that problem, what you end up doing is compute the road network for the entire world. Like Europe, Asia, whatever. You compute the entire road network of everywhere. Once you do that, can you answer the question of how to drive from Salt Lake City to Boston? Yes, of course. But is it really necessary to do that? No. If your goal is to drive from Salt Lake City to Boston, you don't care about any road network in Europe. As far as I know, there's an ocean in between. As far as I know, you cannot drive over an ocean yet. Right? Maybe one day you can, but as it is now, you cannot drive over an ocean. Does that make sense? So that's kind of the analogy I'm giving you here, right? That road network for the entire world is F closure. All possible connections to go from anywhere to anywhere. And the attribute closure is concerning how to go from Boston, how to go from Salt Lake City to Boston. Once you get the road network of the entire world, of course you can solve that problem, but it's an overkill. It's not necessary to do so all the time. Does that make sense? I hope you follow this metaphor, right? So that's essentially what we're doing. Nevertheless, it helps us understand the problem at hand. Okay? When you don't know how to solve a problem, you look for the most naive solution. At least you have a solution. This reminds me of this joke, right? I don't want to go down, but since I mentioned, it's like Trump made fun of Obama, right? Like, you're gonna be the worst president ever. Obama put a mark, and let the mark job said, at least I will go down as a president. That's kind of the joke, right? So it's essentially that's what we're doing, right? It is a naive solution, but at least it is a solution, right? It is a solution. The question is, can we do better? Right? Can we do better? The answer is yes, we can do better. So how we can do better? That's essentially what this slide is telling you. I'm not going to ask you to read the slide right now. You can review this offline. What I will tell you is using an example to illustrate this more efficient algorithm, meaning that to compute. Now our objective is to compute So our objective now is to compute the closure of an attribute or a set of attributes without computing F closure, right? Without computing F closure. So that's the objective, right? Otherwise, we have a naive solution. You compute F closure, you always have a solution. But that's very expensive in certain cases, right? So how do we do this? Well, the idea is, the basic idea is you start with the algorithm proceeds in iterations, and you start with X and F. You start with F and X, and what that tells you is the closure of X is at least X. That's trivial function dependency, right? By X determining X, you have at least this. You have at least this. Do you follow this? Now, using X and F, as well as the inference rules, any of the inference rules we have talked about, the three basic rules plus the additional rules we have derived from the three basic rules, you basically keep adding my apologies for the color, right? I will make sure I get new depends after this lecture. So you keep adding attributes to the right-hand side of this. Using X, F, and all the inference rules, you basically keep adding stuff to the right-hand side. Okay? What are those additional attributes that I can add to the right-hand side? Well, anything that can be derived or can be determined using the existing right-hand side can be added to the right-hand side. So it's kind of like a recursive argument. And imagine, essentially, it's kind of like a treasure hunt. Why is it like a treasure hunt? I give you, suppose you have a sequence of rooms. Each room may have some treasures. I give you the key to the first door. You open that first door. You get the treasure in that room, obviously. But if you are smart, you won't stop right there. You will look for keys in that first room that may open other rooms. Does that make sense? So you get additional treasures. So not only you're looking for treasures, but more importantly, you're looking for keys to open other chambers or rooms to get additional treasures. Right? That's what you do in a treasure hunt. Our algorithm is just like a treasure hunt. I'll give you a key. Initial key is X. Just example. Then you keep looking for keys to open additional rooms. Along the way, you add treasures you found, which is those attributes determined by the current right-hand side. Those are both the treasures and keys to additional rooms. That's essentially what you're doing, just like a treasure hunt. Do you follow that? So that's essentially this algorithm. So let's look at this algorithm in action. How do we carry out this algorithm? Let's say we have A, B, C, D, E as a schema, and I give you this F. And I want you to ask, is B determine E in F closure? Is B determine E in F closure? Well, the naive solution to answer this question is to say, in other words, imagine the row network example I give you is that I give you a bunch of row segments, row network segments, like Salt Lake drive to Provo, Provo drive to Denver, Denver drive to Washington, D.C., and Washington, D.C. drive to Boston. Then I ask you, is there a row connecting Salt Lake City to Boston? In that case, yes, the answer is yes, but you have to figure out this chain of reaction to answer yes. In a smaller scale, this problem is very easy, but on a complex network with many connections, this becomes hard. Right? That's essentially what's going on. Now, in order to answer that question, you say, okay, fine, I can answer that question, but let me compute all the possible connections from the given set of row segments you give to me. Meaning I obtain the entire row network of North America, then I come back and answer, is there a row connecting Salt Lake to Boston? Meaning is B determine E. That's solution number one, which is the solution we talked about, right? You compute F closure. But that can be really expensive, right? Depending on, of course, depending on the setup, right? So we don't want to do that. Let's apply this treasure hunt. In other words, B determine E if and only if what? If E is part of attribute closure of B. These two problems are equivalent, right? If B determines E, then E must be an attribute from the attribute closure of B. Or in other words, if B's closure contains E, then B must determine E, because that's the definition of attribute closure of B. So instead of computing the closure of F and check if B determines E, we will just compute the closure of B using the algorithm we just talked about, which means you start with B, like the first key you have, like a treasure hunt. That's the first key you have. That's the only key you have. And then you look at what other rooms I can open, meaning what other attributes I can determine. Well, from this, obviously you have B determines CD, right? So immediately you got BCD. You expand the closure of B to BCD. You open two more rooms in some sense. That make sense? You follow this procedure? Now you have more keys. Now at this point you have not just the key of B, you have BCD. You have three keys in some sense. So you look at what other rooms you can open using these three keys. Then obviously you also have A, right? Because B determines also A. So you add A to it. At this point, what do you have? You have D determine E, and D is part of the closure of B. Using transitivity, you get E added to the right-hand side as well. So by this point, you can stop. By this point, you can stop because E is part of the attribute closure of B, which means that B must determine E.
Was B determines CD? Can you split that up into B determines C and B determines D?
Yeah, of course. That's one of the rules we talk about. It's the decomposition rule, right? We actually prove this, right? If X equals Y data, you have this. Okay, so that's a simple illustration of this algorithm. Let's try another one. Let's say I ask you, is D a key for the schema R? Essentially, to calculate the closure of D. Meaning that if the closure of D has all the attributes of R. So you start with D determine C, so by transitivity you get DEC. By this point, you cannot go any further. Right? There's nothing more you can determine from DEC. There's nothing more you can determine from DEC. But looking at the closure F, you stop, you claim D must not be a key for the schema R. Is AD a key? We start with AD. Why? Because earlier we showed that B determines everything else by the fact that B is in the closure of AD. By transitivity, it must have AD determine everything else. Does that make sense? Two questions. So he's first. I will ask him to go first.
So is it a super key or is it?
I'm gonna very good. That's the next point I'm gonna discuss. Yeah. At least for now, we know AD is a super key. At least it's a super key. Because B is part of your attribute closure, and B determines everything else. So AD at least is a super key. Now let's answer whether AD is a key. To answer whether AD is a key, what you have to do? You have to check the closure of A and closure of D. We already have the closure of D. So we know D is not a super key. D is not a key. So all we need to check is closure of A. And what's the closure of A? A doesn't determine anything. The closure of A is just A itself in this example, right? So in this case, we have what we have. We have B's closure is everything, and AD's closure is this. Combining this, we know, right? And we also know B's closure is just BCE. And A's closure is A, but nothing else. Using these three facts, we know AD is a key. AD is a key. You follow this rationale? B determines D, but I don't see how you get the conclusion of B determines A. Where did you get that from?
B determines A? Oh, I thought it was the point above. See how?
You're talking about D, right? Oh,
B. Like B.
Yeah, B determines everything else. Yes.
Yeah. So I guess the confusion stems from the fact that B determines the key AD. Like that's confusing to me. Or does that not matter?
Excellent observation. What she's saying is the following, right? So she's not challenging this argument here, which is AD is the key. She's fine with that. But she is challenging the fact that B determines everything else. So it seems like you have a loop. That's what she's saying, right? Which means B determines AD, and AD also determines B. Seems like we have this loop. That's her observation, which is a correct observation. Is that going to be a problem? that going to be a problem? Well, it's not going to be a problem. Think about it, right? It's kind of like saying student ID determines login and login determines student ID. But both of them can still be key of this key. Right? So this interdependency among keys, that's okay. It doesn't give you any trouble actually.
So do you just choose which one is primary?
Yeah, in this, excellent. In other words, we start to identify by this time 2 keys of the schema. And now with that being said, you can choose one of them as your current key, the other naturally become empty. Okay? Now, is ADE a candidate key? Well, this becomes trivial to answer, right? Can someone tell me, is ADE a key?
Yeah. Because you're adding.
It's a super key. Is it a candidate key? Or is it a key?
No.
No. Why?
Because AD is a key.
Yeah, because ADE. ADE, obviously the closure of ADE start with ADE by the fact that AD determine everything else. You know, this infer that ADE, the closure is everything. Which means ADE is the super key, but you have a subset AD, which is a proper subset of ADE, which is a key. It means that ADE can only be a super key, but not a key. Right? So that's it. That's the discussion on function dependency. We're done with it. So we see the usefulness of function dependency through our discussion, but there is one thing that we cannot skip over. And we never formalize the way we handle that problem, which is the decomposition, which is how we decompose a relation when there is a problem. Right? In particular, going back all the way to this example, we know that R determined W for this example is going to be causing a lot of problem for us. And we said the solution is to decompose that into 2. Then we're done. Right? Decompose that into 2, we're done. That's what we said, right? That's what we said. And back then I said, in most cases this is fine, but there are cases where this will actually break down. And you have to do this carefully. That's what I said back then. I never really explained what do you mean by be careful. Like it's like in a really dangerous situation, your friend call you, hey, watch out, be careful. Naturally, your response is, fine, I will be careful, but careful of what? Watch out for what? You have to tell me what, right? What to watch out for. So now we have a full understanding of function dependency. Now is the time to come back and revisit this, and then after we cover this, we're done. We're done with function dependency and normalization. That's kind of as radical as we go in this course. Right? The remaining topics will back to more system-oriented discussions. What's the problem if I just do this? If I just do the decomposition, what's wrong with it? Well, there's a whole set of theorems and arguments I want to show you, but all this definition. I'm going to skip this definition and head directly to this problem, decomposition. Right? That's what we said. You decompose this. Illustrate what the problem is using a real example, then come back to the earlier slide that I just skipped with the theoretical treatment of the problem. Okay, that's how I'm going to do it. Okay. In the earlier case, that's what we have. You have this, you have R determining W, and what we said is to fix this problem composition, you end up with 2, and you're done. The sanity check. To check if your decomposition works or not is to join them back. and see whether you get the original instance back or not. If you do, means that you're fine. Because essentially what you're saying is, instead of putting them all into one table, I'm going to separate them out to two tables. But when you join them back, you get everything back. Everything is fine. And while fixing the problem. So let's check if that's the case in this particular example. If we do a natural join of the two, you do get the original instance back. So there's nothing wrong with this decomposition. It's fine. You got nothing less, you got nothing more. Your boss still gets to pay his or her employees as he was or she was doing originally with respect to the original table. He or she is not paying a penny less, he or she is not paying a penny less, a penny more. So it's fine, perfectly. Does it make sense? However, this doesn't hold all the time. It's kind of like magic, right? I'm always fascinated by this observation. Right? You thought it's fine, but it's not okay in certain cases. Let's look at, again, a simple case, A, B, C. And suppose I have function determinants A determine B, and C determine B. Okay, A determine B, and C determine B. And it's easy to check for this instance, those two functions determinants hold, right? Because you don't even have two records with same value of A, and you don't even have two records with same value of C. B and C determine B naturally hold on this particular instance. Do you follow this? But this definitely raises issues, right, with all the problems we had observed for RDB means that you're going to have update insertion for R determinant W. Why? Because if I add another record of ABC, if I add another record here, I hope it's easy for me to. Okay? What can you claim of the value B here? It must be 2. You have no choice, but fitting a value 2 for it from B. So I can do whatever on C, right? So I still have total freedom on C. Let's say I do that. Does it make sense? But because of A determine B, if I choose to delete both records from this table, I lose that association between value 7 and value 2 forever. Meaning that if I delete this, now, then later I add another record with value 7 for A, I do not know what should be the value for B, because I lose that association forever. That's the same problem as we have observed for rating determining wage power. Right? If you delete a particular association of rate, of rating and wage power, you do not know how to pay your employee in the future. So you have the same problem as before, right? That's kind of why I'm doing this. Okay, the motivation for this discussion. Now, so to fix this, what I will do is, you say, okay, because that observation fine, I'm going to decompose this into two relations. In particular, I'm going to decompose into AB and BC. AB help me preserve A determine B, meaning any association between A and B now is preserved. And BC help me preserve any association between C determine B. Seems like a natural fix. Right? By decomposing ABC into AB and BC, I preserve both dependencies and I preserve the association of those values. Everything is fine. Everything seems to be fine. But is it really okay? Is it really okay? Well, let's, yeah, go ahead.
You can also need the B because B to make sure that they're the same.
B determine?
B.
B determine B, but that's obviously reserved in B and
They're
BC. Right? That's just a trivial function dependency. So the challenge is when you join them back, let's say we do a natural join of the two. What should you get back? What do you expect? You expect the original ABC, right? I did nothing. It's kind of like I give you a few records, I break them up into two tables, and I didn't introduce any new record. I didn't delete any record in the process. I should, of course, get the original instance back, right? What do you expect? Do you? You don't. You don't get the original instance back. You get additional records. You got additional records. This obviously is not okay, right? Imagine this is the payment database, right? You tell your boss, hey, I took this database class. I'm really good at it. And I tell you, your table has a problem. Your payment table has a problem. You explain to him or her the problem. He and she said, oh, seems like that makes sense. You're a smart dude, right? Let's decompose the table. You decompose it. Now your boss end up paying two more payment records. Of course, he or she is not going to be happy with that. Does that make sense? In solving a problem, you end up introducing a more serious problem. That's essentially what it is. Do you follow this example? So decomposition, you need to do this carefully. That's the gist of the story, right? That's the gist of the story. So something goes off in this process. Something's wrong. We need a theoretical treatment of this. We need to, in other words, we need to have a systematic way rather than just do this in an ad hoc fashion and hope everything's fine. Unfortunately, if you just do it in an ad hoc fashion like what we've been doing, sometimes it's okay, like the really determined wage example. Sometimes it's not okay, like what we have here. And we need a systematic argument to guide us through the process, rather than just do this in an ad hoc fashion. Does that make sense? Okay, you may wonder if you're a pessimistic person. If you are a pessimistic person, by looking at this, you may quickly jump to yet another conclusion, which is, oh, maybe there's cases where it's just impossible to decompose. Right? By looking at this, you may, if you are pessimistic, you may argue this example, this particular example, no matter how you decompose, you will never get it work. In other words, is there another way to decompose the original relation and fix the problem we have with insertion, deletion, and update anomaly, and still get this nice result? Joining them back will give you the original relation. It's possible to do so. In this case, yes, it is possible to do so. I'm going to use the same example. This is the same example, exactly the same example. Instead of decomposing to AB and BC, what I will decompose to is AC and BC. And by joining them back, I get the original instance back, ABC. However, there is a problem with this decomposition as well. Yes, I think somebody observed that already.
Don't you lose the relation between A and B?
This decomposition to enforce that. Now it's become much harder to enforce that because A and B are in two separate tables. You need to do a join to enforce A determine B. Do you follow this? However, that means that this is still better than the earlier solution because the earlier solution is simply wrong. And this solution at least is correct. It only makes our constraint checking more expensive, but it's still doable. Even B is quote-unquote lost in this process. Lost in the sense that it's no longer. You follow what I'm saying? Joining the decomposed relation back do not give you the original instant. Do not give you. All these discussions, I will only touch base the basic concept of normalization. I don't want to go into deep discussion on normalization. If you're interested, I will highlight the part from the slides I will cover. I will also refer the remaining part for you to read of your own interest, but it's not part of this course. In most commercial engines nowadays, by the way, once you supply a set of functional dependencies, it can automatically conduct normalization for you, meaning it can automatically fix all these problems for you. Most engines have that capability nowadays. Meaning that as a DBA, database administrator, you actually don't have to fully understand what's going on. You just specify the set of Arduino function dependencies and click a button somewhere, magic happens. A computer program runs beneath the engine, fix the problem for you. But that being said, it's still good to have some sort of understanding what's going on, even if you have a magic button. That make sense? Okay? That's essentially what we're doing here. Right? Try to understand what's behind the magic button. When you click normalization in a commercial engine, what happens? What really is going on? Of course, you say, I don't care. I know the decomposed relation and a bunch of deducted function dependency, I'm fine. Yeah, yes, you are fine, because commercial engine does a really good job. They pay a bunch of developers who earn really high salary to make it right. Right? But as a DBA, it's still good to know what's going on, right? If you really want to manage your database under all circumstances. So that being said, this is a fairly deep topic. So bear with me. I will try to make it as intuitive as possible, as easy to understand as possible, and I will choose to cover only the basic concepts without going to all the deep theoretical results behind it. Because this stuff can be, because there are so many different possible cases, a lot of corner cases can make this discussion really tricky to understand. So I will focus on the most basic ones and refer to the remaining ones for you own to read. But it's not covered for this course. I will, of course, make it clear what's covered and what's not covered in terms of what to expect in the final. Okay, if that's what you care. All right, that being said, let's rewind. Come back to the theoretical treatment of this problem. Okay, so now we have, at least all of us have I hope all of us by now have a really good understanding what the problem is, what we're trying to solve, and the next step is how to solve this problem, right? How to solve this problem systematically. How do we solve this problem systematically? That's what we're going to do next. Formally, this problem is called normalization. Normalize your schema right to the problem we're trying to solve. And there's a review of function dependency, which I'm going to skip. So to understand normalization, I thought there was a problem somewhere. But you had a problem?
Yeah. So just a quick question, like why don't we decompose into 3 tables? Like A, C, B, C, and A, B.
In the early example, can we decompose into 3 relations? I will defer to answer that question later on after we talk about the normalization. That makes sense? That's kind of a quick answer to you guys. Now, so normal form is a concept that people use to quantify or describe what kind of state, in what state you schemas satisfy. Okay? In particular, first normal form is very simple. First normal form says all attributes are atomic, meaning that I do not deal with set attributes. I do not deal with set attributes. When I say color as an attribute, that means a single value for that color attribute for all my records. I do not have a record where color is a set, meaning that I have red, blue, and green. That's essentially when you have this condition met, then your schema is called satisfying the first normal form. So first normal form is really simple. By default, in our course, we are assuming that all schemas are in first normal form, meaning we do not have set values attribute. We do not have set values attribute. Okay, that's first normal form. That's really easy to understand. Second normal form is of only historical interest. People rarely mention it nowadays, so I will drop that discussion. Third normal form is something most relational schema nowadays, most commercial designs will try to satisfy this particular normal form. Third normal form. By the way, the way you read this is first normal form has only one condition, which is all attributes are atomic. Second normal form essentially take that condition of first normal form and add additional constraints. Henceforth, whatever schema that satisfies second normal form will automatically satisfy the first normal form. That's why there's a superset relationship between first normal form and second normal form. Then similarly, by adding more constraints to whatever you have on third normal form, you get second normal form, you get third normal form. Okay, so on and so forth. Okay, the most restrictive normal form people use in practice is called Boyce-Court normal form, BC and F. Boyce and Court are the last name of the two persons who identified this particular normal form, who defined this normal form and provided rationale for it. So what we will do is we will start with this BC and F, and we will talk about third normal form briefly and ignore the other normal forms. We will focus on just these two, and in particular we will give a really detailed analysis of BC and F and give just a kind of introduction to third normal form. Why? Because third normal form is actually, compared to BC and F is much more difficult to analyze, to analyze. So we'll focus mostly on this, briefly introduce here, then we're done. Okay, with this discussion. So what's BC and F? Okay, let's first look at the definition. The definition is very simple. Given a schema R and function dimension F, what I require is the following. For all functional dependencies in the closure of F, meaning that anything you can derive with respect to this schema, one of the following must be true. Either X determine A is a trivial function dependency. Trivial function dependency means that the right-hand side is a subset of the left-hand side, like AB determine A, or ABC determine AB. Okay? Either it's a trivial function dependency, or X is a superkey. In other words, other than superkey constraint, I do not have any constraint on my schema. If that's the case, my schema is in BC and F. So this actually is a very simple definition, right? This is actually a very simple definition. In other words, what essentially you are saying is, I only have key constraint. I only have key constraint, I don't have anything else. By the way, whenever you have a key constraint, you naturally have a bunch of super key constraints. You follow that? A determine A, B, C, D, E obviously means A, B determine A, B, C, D, E, A, C determine A, B, C, D, E, and A, C, D determine A, B, C, D, E. Why? Why? Because by transitivity and trivial function dependency, right? Whenever you have something like, suppose X is a key of R, what that means is X determines every attribute of R. Right? That's essentially what it means. And of course also means that none of the subset of X has this property. So that's when I say X is the key, it basically implies the two things. Does that make sense? Right? And now if I add any Y is a subset of R. If I add X, Y to X, what do I have? By trivial function dependency F, X, Y determine X. That's just a trivial function dependency. X determine everything means that now by transitivity it means that X, Y determines everything. So in other words, a key constraint implies a number of super key constraints. A single key constraint gives you a number of super key constraints. This Y can be anything. This Y can be anything from R. Does that make sense? Do you follow this? So that's essentially what we have. And BC and F basically says you only have key constraint, or in other words, you only have super key constraint. You don't have anything else. Whatever you have is either a key constraint or trivial function missing. Why, you may wonder, okay, that's simple definition, but why you care about this? Why you care about this definition? That's because when you have this definition, you can show that your schema has no redundancy whatsoever. And that's the key. That's the key. That's the key why people define BC and F in this particular form. You have no redundancy whatsoever. Let's look at a particular example. Assuming I have a simple schema X, Y, and A, and I give you an instance like this, where I have one record X, Y, 1, and A, I have another record X, Y, 2, and question mark. Now, I also tell you I have a functional dependency X determine A. X is this attribute, A is this attribute. And suppose that's the only attribute, that's the only constraint I have. That's the only functional dependency what I have. You follow this? If that's the only constraint you have, is this schema in B, C, and F? Is this schema in Boy's court normal form by the definition? Is it in or is not in? Yes, it's not in B, C, and F because, first of all, X determining A is not a trivial function dependency. A is not subset of X. Secondly, X is not a key. If it's not a key, it cannot be a super key. X only determines A. X does not determine B. So X is not a super key. Henceforth, X determining A has violated the definition of B, C, and F. Do you follow the rationale? So it is not in Boy's court normal form. You may wonder, so what? Well, when you are not in B, C, and F, you will have redundancy. That's the power of this definition. If you're not in B, C, and F, you must have redundancy. What is the redundancy here? What's the redundancy here? In particular, what can this question mark be? What can this value be? You have no choice, but only A. You have no choice with this question mark, but filling a value of A. You have only this choice of A. You only have this choice of A. You don't have any other choice. You follow this? And that's the redundancy, by the way. Once you have redundancy, you suffer from all those problems we talked about, insertion, deletion, update, anomaly. Once you have redundancy, you suffer from those anomalies we talked about earlier. You follow this? So this simple example illustrates to you why people define B, C, and F as the way it is. Of course, I didn't give you a formal argument, right? There actually is a proof shows that if you define B, C, and F in this way, meaning that either you have trivial function or you have key dependencies, you have no redundancy. You need to have a formal argument to show this, which I will skip for this class. Okay? We skip that proof. But there's a proof to show that if you have these two only, then you have no redundancy. You follow this argument? So I'm not going to show you that proof, but take that as a fact. Right? Take that as a fact. Meaning that if you have B, C, and F, you have no redundancy. Your schema is as quote unquote, as clean, as concise as possible. Everything you store. In other words, every single bit of what you choose to remember is necessary. Every single bit that you choose to remember is important. If you lose a single bit, you cannot reconstruct that single bit from an information theoretical point of view. If you lose a single bit, you cannot recover that information. I'll give you a real example, right? I hope, can relate to the three statements I made here. If you can't, I think you have a problem. All of you should be able to, right? So all of you think, this is in my brain. But wait a minute, your brain may not function this way, right? Your brain may look at this, at least my brain look at this, will say, okay, if those are the knowledge I have, my brain has limited space. What I would remember is, I remember this. I only need to remember one of these two. You follow what I'm saying? At least that's how my brain, I hope that's how my brain works. I don't know, right? But the thing is, if you may argue this, like, what's the point of this example? Well, the point is there are simply exponential number of knowledges out there. If you choose to enumerate everything, in other words, you're building a huge, huge hash table out of your brain is not going to scalable. Your brain is only this big. Right? Your brain is only this big. And you cannot scale beyond certain scale, right? If you choose to remember everything. So what you do? You use a keyword called deduction. You deduct new knowledge from existing knowledges. And that deduction works if you choose to remember things correctly. In this case, I can remember these two, or remember these two. But if you choose to remember only these two and ignore this, you are losing knowledge. You are losing knowledge. Does that make sense? But this is nothing else. If you formulate this is kind of like a functional dimension example, right? So that's essentially what BCNF is trying to tell you, which is the minimum set of knowledge you need to remember, yet without losing any critical bit. Get rid of any redundancy that potentially you have in your brain. Does that make sense? So using this, I hope using this simple metaphor, analogy, whatever you call it, you can kind of relate to what BCNF is trying to do. Okay? You can try to figure out what BCNF is to do. Do you follow this? Okay. Cool. All right. So that's BCNF. In practice, unfortunately, not all schemas is gonna be in BCNF. Not all schema are gonna be in BCNF. And when that happens, you have redundancy. And the way you're gonna fix that is to decompose that into smaller relations, such that each relation is in BCNF. Such that each relation is in BCNF. That's what you try to do. But as we have seen from the earlier example, decomposition, if you do not do it carefully, may lead to wrong knowledge. Okay, so you have to do this carefully. So how do we do decomposition? That's essentially the next question. How do we, this is the formal definition of decomposition. Now we know what decomposition is. I'm going to skip this definition, right? Basically, you have a schema R, which is the set of attributes. You basically break up the schema R into two smaller schemas. Each has a subset of attributes, and the union of the two smaller schemas cover all attributes of the original schema R. That's essentially a decomposition. Meaning, in the very least, when you do decomposition, you don't lose attribute. You start with A, B, C, you do not decompose into A and B. In that case, obviously, you cannot recover the original schema because the attribute C is lost. That makes sense? So that's the basic definition of decomposition. So in other words, every attribute of R is represented in one of the new relations. So looking at this particular example, now we can formally argue why R determined W is giving us so many problems. Why? Can someone tell me why R determined W gives us so many problems? Because R determined W has violated the definition of BCNF. We have two functional dependencies in this case. One functional dependency is S determining everything else. Is that okay with respect to BCNF? The answer is yes. Why? It's not a trivial function dependency. However, it's a key constraint. Right? S determining everything else means that S is a key. In other words, in this X, by the way, X determine A in this definition, both X and A representing not only a single attribute, but a set of attributes. But of course, they can be a single attribute, because a single attribute is also a set. Right? A single attribute is also can be viewed as a set of a single element. So X and A here are two generic symbols representing a set of attributes from R. That's to be noted, right? That being said, S in that example of S determining everything else, security number determining everything else, your S is your X. Everything else is this A in this definition. Everything else, meaning that the left-hand side is the super key. X is the key, S must be the super key. Henceforth, with regard to the definition of B, C, and F, S determining everything is okay. It does not violate B, C, and F. So that's okay. However, if we move on to the second functional dependency, which is R determine W, we have a problem, right? This is your X, this is your A. And to satisfy B, C, and F, there are two ways to satisfy this, right? One is A is a subset of X, or X is a super key. Note that it's or, right? You only need to satisfy one of, not both. In other words, what we're going to check is W a subset of R? Obviously not. W is which power? R is reading. Which power obviously is not a subset of reading. So the first condition, false. What about the second condition? Is R a key or super key? Obviously no. Reading only determines which power, reading doesn't determine anything else. You follow this? Which means this is not in B, C, and F by the earlier, but just as the same as in this example, this implies that we're gonna have redundancies. Once you have redundancy, all this is normally gonna occur. It's kind of like you are remembering all this knowledge. You are remembering redundant knowledge. If that's all you care, it's probably okay, but your brain has so many things to remember, eventually you're gonna run into a problem to do this. That's kind of what's going on, right? Intuitively, that's the way to understand this, okay? You follow this? Henceforth, we decompose this into these two. Now, why, after decomposition, this is okay? Let's look at the two new schemas. One is SNLRH, one is RW. What are the functional dependencies that hold with respect to each one of them? The only thing that holds here is S determining everything else. That's still okay. That satisfies B, C, and F requirement. Why? Because S is still a key of that schema. Right? So the first schema is in B, C, and F. What about the second schema? For this schema, the only functional dependency now you have is R determine W. Is this now in B, C, and F? Oh, magically now this is okay because R determine W means that R's closure is RW, means that R is a key. For this new schema, R is a key for this new schema, so this new schema is also in B, C, and F. So henceforth, your decomposition is okay. Back then, we only know it's okay by looking at it. Now we formally know why it's okay because both decomposed relations are now in B, C, and F, so that there's no redundancy whatsoever. Your brain is remembering the minimal set of knowledge without losing anything. Do you follow this formal argument? Okay. You may wonder, okay, if that's the case, let's check this example I gave you guys earlier, right? We said, okay, this problem, this particular example is bad. We decompose it. What's wrong with the decomposition? Let's look at it. I will introduce the problem and come back on Wednesday to explain how to fix it. First of all, A determine B and C determine B means that the given schema is not in B, C, and F. Why? Both functional dependencies actually have violated B, C, and F requirement. Looking at A determine B, is A a super key or key of the schema? No. A only determines B and A. A does not determine C. So A determine B has violated B, C, and F requirement. In other words, A determine B will introduce redundancy for you. Same argument holds for C determine B. C determine B implies C determine B, C, but C does not determine A. So C is also not a key constraint. So both functional dependencies in this case have violated B, C, and F requirements, meaning that if you go with this design, you end up with tons of redundancies. Okay? So you have to split them. So you do. You decompose them. You decompose them into natural A, B, and B, C, and you check. It doesn't work. But an interesting observation is the two new schemas, A, B, and B, C, are actually B, C, and F schemas. With respect to A, B, the only functional dependency you have is A determine B. At this point, A determine B is no longer a problem. Why? Because A is a key for AB. A determine B means A determine AB. Similarly, for the schema BC, your C determine B means that C is a key. C determine B and C. So we reach this seemingly dilemma, right? Seems that we got two B, C, and F schemas, which is fine. But how come by joining them back we don't get original instance? What this example shows you is simply decomposing the input schema that's not in B, C, and F into smaller schema that are in B, C, and F is not enough. We need something more. We need something more. That something more is what I'm going to continue on Wednesday, and hopefully I will finish the discussion. Okay?
I thought it was going to feel like your logic was wrong or something.